During this pandemic situation, there are restrictions for contact classes. But interestingly, the possibilities of new knowledge through the online media are increasing. It is the right time to utilize these opportunities. According to my knowledge, the subject of today's discussion is very relevant and its traces were seen only from the end of 1990s. That itself shows its importance. When I Googled, I got the definition of edge computing as a distributed computing paradigm that brings computation and data storage closer to the location where it is needed to improve response times and save the bandwidth. I'm not the right person to say anything more. We have with us Sri Biju Thomas, who is really an expert in this field. Once again, I welcome you, sir, and conveying my sincere gratitude for accepting our invitation. I wish all success to the program. Thank you.
Thank you, Raksa. Now, I welcome Mr. Biju Thomas Emsa to conduct a webinar on edge computing.
Thank you, Aparna. Am I audible?
Sir, yes, sir.
Okay. Thank you. So good afternoon, everybody. Respected Principal Dr. Raksa, Anup sir, other professors, dear students. A very good afternoon to you all. Just give me a moment when I actually set up this presentation. Is the screen visible?
Yes, sir.
Okay, good. So, good afternoon once again. So today I will be talking about edge computing. And Aksar gave that crisp explanation or the definition of edge computing. So thank you, sir, for that. So just, it's an afternoon and it's always a good time to dream, right? So first let me take you through a dream. So my first question is what is your vision for the future? Especially from the area of computing, how we can make our life easier and more comfortable. So I just captured a few thoughts which is to some extent available in today's environment. So the first one which I want to take you through is the retail industries. So all of you might have got this experience of shopping in the supermarkets, right? So when you get into a supermarket, there are separate aisles kept for different category of products, and for each product, in that group, different products of different brands are being kept. And the customers come and pick the choice of his or her liking. So from the supermarket side, they always keep the monitor the supply chain and ensure that the racks are again filled and the product is available over there. Now, we will always have this data about which product is moving, which one is having more sales. And then, you can slice and dice that data and then get all these marketing information like, what group of people each brand is more preferred, like the gender preferences, the age preferences, the regional preferences, the seasonal preferences, you name it. I mean, you can get all those information about how these products are actually sold out. Now, do you really get that information as a retail shop owner of why people are actually choosing one brand over another? Or put in another way, do you get that information why a person reject one product in compared to the other? Because we all have done that thing, right? We have gone into the supermarket, we have taken the product, we have just compared it, we'll just look at it and then finally decide okay, this is not good for me or this is good for me, and we pick it up and then we come out. So, but is there any way at present possible to collect that information? Why people reject one brand over the other? That's a key information as far as a product is concerned, from the manufacturing side, from the product side, from the retail side, from all those aspects. This information is very important. Then only they will be only if you understand the flow, you will be able to understand the defects or the deficiencies and then correct it and make it a better product. So how will you do it? So that's a key challenge which is faced by the retail industry. So when you compare this supermarket experience with an online shopping, what difference do you see? If you buy a product from Amazon or Flipkart or that sort of an online market, what is the difference? The key difference is that in an online experience, in an online shopping, the online portal is keeping precise logs and tracks, like what all products you have seen before, what all are you comparing, what all are you looking at, and finally they will be able to say, like, which product you have bought it, right? So that complete experience is captured with the online shopping experience, and this is a key difference. And when you see the picture on the right side, the Amazon Go shops, so these are the new novel cashier-free shops which Amazon has set up, especially in the US region and all of Europe and US region. So what's the difference over here? Here, the customers come in, they take a trolley, they just move in, they pick up whatever items they want, they just drop it into the trolley. When they drop it in, that will get added on to their cart, and then when they actually move out, the amount is debited from their Amazon account, and they just walk out. So that's their tagline also, just walk out. But beyond this, on this trolley, on the shop, there are multiple sensors which are kept over there. There are multiple cameras which are kept over there, which precisely measure, which precisely track your movements, what all you are doing in the shop, how you are actually picking up things, how much time you spend at each aisle. All those information is actually captured over there. So the difference is, like, from the normal traditional supermarket, when you actually go into a Amazon Go kind of a supermarket, all these sensors and connected devices, they are actually monitoring all the data. There is so much of additional data which they capture about you, which they can actually use in the betterment of the shop or the product, right? So that's the key message when we actually think about the retail industries. Now let us take another example, which is basically an extension to the concept which we described earlier. So this is basically the vision for the safer cities in the future. So a few years back, there was an incident in an ATM in Bangalore, and then after that, the Reserve Bank has come out with a mandate that all the ATMs should be having a security guard and all. But more than crimes which actually happen over there, there are a lot of ATM thefts, financial haste, and all those things which have happened based out of ATMs. So how do you identify it? So a normal person who actually goes into an ATM, the way in which he will transact over there, and the way in which a person with a hideous interest is coming out and he will be behaving. So there is a subtle difference over there. So if you can constantly monitor the behavior of the person who is in the ATM, and then do some modeling or do some analysis on the way in which he is actually behaving, then you will be able to analyze and then come out if there is any abnormality with the behavior demonstrated by that person. And if there is any abnormality, then you will be able to alert the authorities, be it the police, be it the bank. You will be able to alert them so that they will be able to take the necessary steps to address it. So effectively, what we are trying to do is here, because the cameras are already there. The cameras are there in the ATM. So we just need to take the feed out from there and then do some analysis on that feed constantly. And on a machine model, you will be able to do that thing, and then you will be able to prevent a crime before the crime actually happens. So that way we can lead to safer cities. And finally, the third aspect which I wanted to share with you is the predictive analytics. Predictive analytics is again an extension of the safer cities concept which we said. prevent an incident before that incident actually happens. So if you think about all these connected world where we actually live in, there is a lot of networking devices, network connectivity is there, cable connectivity is there, and think about how a customer will behave or what the customer's experience will be if you have unstable network connectivity. And that's not an expected behavior from an ISP, right? So for the, as far as the ISPs or the internet service providers are concerned, they are always focusing on how I can provide a disruption-free service to the end user. And for that, what he can do is like he can always monitor some vital parameters on the routers or on the set-top boxes or on the connected device. So that it could be very minimal things like how much memory you are using. Is there a memory overflow over there? What is the heat? What is the temperature of the device? Is it going overboard? What is the CPU throughput? I mean, is there any abnormality in the CPU throughput? So these are some of the very minimal things which you can constantly monitor. And if there is any abnormality in that value, then you know something is going wrong. And in that case, you can take the necessary actions over there. Maybe like restarting a process or kicking off a self-heal script, which will actually take care of all these things. So effectively, what you are trying to do is you are trying to prevent an incident before it actually happens as an incident. At the moment it starts showing the symptoms of that incident, you actually pull it out and then take the necessary steps. And this step is actually called telemetry, where you collect the vital parameters from a device, do some analysis over there, and then take the necessary corrective action. And believe it or not, the telemetry is already included or incorporated into our browsers, our OS operating systems, mobile phones, all these things. And interestingly, it is capturing all the information which we are, whatever we are browsing on the net, it's actually capturing. So to what extent it is actually sending it to the server and then doing the analytics over there, that only is varying depending upon the permission which we are giving it. But effectively, all this information is currently tracked, and then it is actually reported, and then analytics is done over there to make informed judgments out from there. So these are the three cases which I have actually taken up for our discussion today. And the key aspect of here, if you look through it, the key aspect here is that there is a lot of data which is getting collected from each of these scenarios, from the retail shop scenario, from the ATM or the safer city scenario, or from the predictive analytics scenario. A lot of data is collected from the end user or the end customer. And this data is actually pushed out to a cloud device. And then in the cloud, which is actually a collection of storage where all the data will be stored, computing where all these computation will be handled, and then finally the analytics part where the machine learning models will be running and deriving out some key value from that data. So this whole collection of analysis, the storage, compute, and analytics is being done in the data centers or the cloud centers, which are in a distant geography, and then connected through high-speed network, high bandwidth data networks, and then you collect that thing, and then you get back that informed value from that cloud computing module to make informed judgments based on that. So if you look at, this model can be expanded into any of these scenarios. Like it can be. We already discussed about the retail. We already discussed about. The other things. IoT will cover a lot of stuff. The home automation, the smart factories, the smart hospitals, the media, like you have the OTT, like the YouTube and Prime and all those connectivity. So all those services where you actually think about it, like the cloud applications, the Gmail, the intelligent assistants like the Apple Siri, or the Google, Amazon's Alexa or Google Assistant. So all these different solutions which we have, they are all currently working on a cloud computing model where you have the data and that data is collected from the end devices, your mobile devices or your connected devices, and that's all consolidated, sent to a centralized repository, centralized cloud data center, which is a cloud storage, and from there the processing is actually done, and finally that result is actually pushed back to you, so that in your end devices, your client devices, you are actually displaying or playing that value or that response which you actually get from the cloud model. So the key point over here is that whatever we are seeing today for all these different applications, it's all working on a centralized model. You have the data, you push it out to a cloud storage. In the cloud storage, which is a huge data center, you do all the computation work and analytics work and all, and finally you respond back with that key value, the key insight which you get, and then that's actually taken for getting the response onto your device. So with that, let's take a step backwards and just analyze the timeline of the computing technology, so that we can see what patterns existed over there and how it has evolved over the years. So the introduction or the beginning of the modern computing technology has actually began with the mainframe computers in the 80s and the 90s. So these were primarily number crunching machines, huge devices, but number crunching machines, which were primarily focused on batch processing, time shared batch processing. And the work was mostly done on structured data. And then the connectivity, it was network computers, but the connectivity was based on proprietary networks like SNA or something like that. And then the bandwidth availability, the throughput was in kilobytes. So that was a luxury at that point of time. And moving on to the 90s, the desktop computers actually came into the existence. And then initially it was dumb terminals, non-graphical terminals, and then slowly it evolved into the Windows came into the beginning, and then the Intel came into the existence, and the Windows and Intel dominated with the multimedia PCs and all. So the important change over there was that the structured text came into the beginning. We had word processing applications, and also that, and these desktops were primarily used as point of sales terminals in the processing financial data in the bank, for HR processing, application processing. So all those kind of information was actually processed in the desktop. And then came the era of internet, where all these PCs were actually connected together, and that came out with a lot of connectivity. And then the key change over there was that TCP/IP became a standard. So that's the biggest advantage, or the biggest value which the internet actually brought in. And then with the internet, in addition to the structured data like the text, we were able to process the images also, and then we started seeing the websites which were initially static, and then it started becoming dynamic, like with the JavaScript and the GIFs and all those things. But and another key innovation which happened over there is the click data, which is HTML, the linking of the pages. So you click on a URL, you are actually taken to that URL. So the rest of the things are all abstracted beneath that, and then you are moving over there. And so all these aspects were brought out in the era of 2010, and that's the time when actually Google started, Amazon started in the e-commerce space, and then the initial social media actually came into the existence. These are Orkuts and all, which actually died down now. And after that, the mobile devices came into existence somewhere towards the end of this time frame, and the decade of 2010 to 2020, which is the current decade, that was dominated by the mobile devices. And with the mobile devices came with the social media revolution. We had the Web 2.0, grid computing, the gigabit bandwidth speed coming in, So in the media, if you look at it, it is not just the text and the images anymore. It's all about video and audio, which is actually going through the network. So if you do an analysis on the network, a major chunk of the bandwidth is taken up by these media files. It could be the video files in the Facebook or the YouTube or Twitter, and then the other aspect is the intelligent assist, like though in the ads we say like, hey Alexa, what is the weather for today, and then so that question which is actually going out and the response which is coming out. So if you just if you just take a slice of the network and then you just look at what is the kind of data which is going through the bandwidth or being occupied in the bandwidth, the major chunk of the bandwidth is occupied by these media and media files. So that this is the era where the cloud computing is actually established itself, because you have all this data coming out, all this data which is getting generated, and it is actually sent to a centralized repository where it is actually analyzed and the response is being obtained back. And this era also came out with a new terminology called big data. That big data obviously means large data, right? So, and what are the three characteristics of that? They are the volume, velocity, and the variety. Volume is that like the huge size of data which is getting generated. Terabytes and terabytes of data is getting generated on a daily basis. And then the second one is the velocity, the speed with which these data are getting generated. And finally, the variety. The different earlier, if you look at the evolution, we can see that it all started with structured data, then it became unstructured data, but we were still processing it after converting it to structured data. But now, if you look at it, it is the major chunk of it is these unstructured, diverse, different types of data which needs to be processed, and then we can do that analysis. So that big data is actually ruling the world, and cloud computing was a perfect solution for big data. But now the challenge is like this data is growing huge, and can cloud computing hold on to this bombardment of the data? So with that, if you do an analysis, the current statistics say that as of today, we have each single person accounts for about a gigabit and a half of data traffic per day. So that's the current volume of data which is generated by a single person today. And then it is just continuing to grow. And it is not just the individual people who actually contribute to this data, but it is also the different connected devices which are actually contributing to it. So if you just think about a connected airplane, so that is generating somewhere around 5 terabytes of data per day. If you think about a smart hospital with all the instruments and the patient data and all those information, that is generating somewhere around 3 terabytes of data per day. If you consider a smart factory with all those connected devices, the smart robots, the conveyor belts, the sensors and actuators, everything over there, that's creating somewhere around 3 petabytes of data per day. And then finally, the connected car, which is the buzzword today. And each connected car is creating 4 terabytes of data per day, per car. So that's a huge amount of data which is getting generated from these devices. And the adoption of these mobile computing and all those things are actually expanding. And by 2025, it is expected that about 75% of the world population will be having a mobile device, and that's accounting to somewhere around 6 billion devices. And another estimate is that every connected user will have at least one data transaction one transaction each every 18 seconds. That's again a huge inflow of data. So the bottom line is like we are just seeing that that vastness or the explosion of the data which is getting generated on a daily basis in the industry, in the world as of today. And the cloud is just reeling under pressure. The cloud alone cannot solve this problem, and we need more optimized solutions to drive that change. just to give some more points about this data explosion. As of today, the current data which is getting generated on a yearly basis is somewhere around 50 zettabytes. And the expectation is that by 2025, in another 5 years, it will be reaching somewhere around 175 zettabytes. And to give you a kind of pictorial representation to understand the volume of it, if one brick is comparable to a gigabyte of data, then 1 zettabyte is equivalent to the Great Wall of China. So that's the volume of data, which we are going to see, which we are seeing currently, and then we are going to see in the next 5 years. So this graph over here shows the real-time data. So we talked about these connected devices, and the connected devices will be sending real-time data. Like think about autonomous car. You're driving a car, and then how much time will you, how much seconds or how much milliseconds will you get before you see a red light, and to decide upon whether you need to, what you need to do, whether you need to stop or you can zip through. How much milliseconds will you get? And then can you think about doing all that thing by sending that data into the cloud and getting the response back? You may be ending up in the next signal, right? So the real-time data, that cannot afford to latency. We need a real-time network operations to conduct that thing, and how it is possible. So the statistics, just to give a statistics, 30% of all the data which is created in 2025 will be real-time data, and that's somewhere around 60 zettabyte of data. Nearly all the real-time data will be coming out from IoT or the connected devices. And unfortunately, these data, the IoT generated data, is unpredictable. Just assume that there are certain sensors in a factory floor, and if unfortunately something happens, maybe a fire, maybe an explosion, and all these sensors will go haywire. They will start firing off. And just think about the amount of data which will be coming over there. So you just cannot predict how much data, the volume of the data which will be coming. So it will just explode. It maybe is like zero also at times. So that elasticity in consuming the data and processing it, that's what is required in the systems which we actually think about for the future. So, and this is the place where actually we need to think about disruptive solutions, and that's how the cloud computing is going to evolve. So currently, as we have seen in an earlier slide, like in the cloud, we have got the storage, compute, and analytics. And as we move forward, what we are going to see is that this data is not going to be, this whole data is not going to be sent to the cloud, but rather it's going to be processed across the value chain. That's the end-to-end value chain. There will be processing done at the device level itself, so that we filter out the unnecessary data. There will be processing done at the edge side, so that we can make some value out of it, and only those relevant data will be sent back to the cloud. And believe me, that itself will be choking the network at the size in which the data is growing. So this is the evolution coming out, and where we will actually spread out the computation, spread out this storage, compute, and analytics pattern across the network. That is the area where the data is getting generated, the area near to the area where the data is getting generated, and also into the cloud. So the cloud will continue to exist, but across the network. And this is basically the edge computing. Okay, so any questions so far? Okay, I hope I can continue. So here is a definition for the edge computing. So edge computing is a distributed computing framework that brings computation and data storage closer to the location where it is needed to improve the response times and save the bandwidth. So if you remember the earlier picture of the cloud computing I have shown you a few slides back, there you saw that all these devices, all the connected devices, all the applications were directly connected to the cloud. And that was a centralized model. And in this model, what you're seeing is each of those devices are connected to an edge, which is marked in yellow over there. And that edge is located closer to the place where the data is actually getting generated, and only the relevant data is being pushed out onto the cloud. So basically, this is the change. I mean, there is one more level of indirection coming in with this computing model to ensure that there is an optimization which is happening on the data volume, which actually gets translated back to the cloud, and the value which is getting generated over there. So that's effectively what edge computing is all about. Now, how can we achieve it? That's a big question, right? So just before getting into how we will address that, we will just quickly look at the pattern, the timeline which we saw earlier, and if we can deduce any patterns over here. So when you thought about the mainframe, so the mainframe was basically a centralized model. It's located at one location. People will go to it, or people will connect applications to it and get the work done through it. And then when we moved on to the PCs and the internet, what happened was that it was basically a client-server model, which was a distributed model. So the data was collected from the clients, and it was actually processed on the server. And then so the server market, I mean, it was a huge boom over there. And then we actually came out with this client-server architecture, the 3-tier architecture. So all those things were basically representative of that distributed model. And then coming on to the next, the cloud, mobile and the cloud devices. So the mobile devices were all connecting to a cloud device. So think about all your applications which you have on your mobile device, be it Gmail, be it YouTube, you name it. Like every single application gets connected back to a cloud server, gets the data done over there, and gets back. So again, the computation actually moved back to the centralized model. And now with the edge intelligence coming in, it's again going back into the distributed era. So I mean, it's actually a kind of pattern which you can see across all the industries. Take the electrical industry or the mechanical industry, and in the computing industry also we can see this centralized computation moving on to the distributed computation, then again coming back into centralized computation, and now again moving back into the distributed computation. And another aspect over here is that if you think about the mainframe, maximum there will be something like 10 million people who might have used. I mean, there could be something like 10,000 mainframes, and each mainframe machine was used by somewhere around 1,000 people. All put together, somewhere around 10 million people who are using it. And then we moved on to the next evolution, which is the client-server model. There were somewhere around 2 billion PCs in the world, and then 2 billion devices were actually in the market connected together. And then when we came into the mobile era, what we saw was that everybody was having a mobile phone. And if you think everybody is having one mobile phone, it's somewhere around 7 billion people in the world today, and the maximum extent of edge devices or the compute devices should be limited to somewhere around 7 billion. But what we see now is that all these IoT devices or the edge devices are coming in, and they are no more associated with a human. They are coming out in bulk, and the numbers are just going to multiply. We are going to see trillions of devices in the next 5 to 10 years in the market. So that's how this computation paradigm is actually growing. Okay, so let's look at why the edge computing is required. So few of the things we have already discussed. The first one was the speed or the latency requirement. You are driving on an autonomous car, and how much seconds will you get to get that response back. And you can't afford to in sending the data on the cloud and then getting back the response. So you need something faster, you need something quicker. So that speed, that's a key factor. The second aspect is the security. When you send all this data out through the network, you are increasing the surface area for the attack. So the more controlled you are, then you will be in a much better position to offer security to your data. And then along with security comes privacy also. Like think about the hospitals and also the patient data and all, or the financial, the bank data. So these are all private and confidential data, and they also cannot be exposed. I mean, how can you send out these data to a public cloud? There are certifications available and things like that, but in the first place, if you're able to avoid doing that, then you will prevent that rather than sending it out and then doing some analysis over there. And the third part is the scalability. The scalability, we have discussed about it. I mean, the number of devices which are going to come into the market, the amount of data which are going to be coming in, and the one key technology which is actually accelerating all these explosion of devices is the 5G. The 5G is coming out pretty fast, and it has a lot of computational and networking capability associated with it, so that it even allows for the machine-to-machine or the M2M communication model. So with the 5G also coming in and working as a catalyst with the proliferation of all these network devices, the scalability of the whole system, like how scalable your cloud solutions, it cannot manage that. So that scalability factor is actually driving out a need for edge computing. And finally, the low-cost ASIC chipsets. So which is the current focus of the chip vendors, associate companies as of today, like the Intels and the Broadcoms and all. So if you just think back, you can just relate to yourself to the CPUs which Intel was manufacturing, or the GPUs which the general purpose units which the NVIDIA was actually manufacturing. Now they are all moving towards an ASIC chipset, which is an application specific ICs, which is made basically for a special purpose. So the key factors are, it is specialized, it is for a specific purpose, and it is very low cost. And that cost factor is that low cost is actually helping in the development of new devices, because the cost of those sensors and the connected devices will be reduced, and then that will actually expand out into the market, and that low cost is actually driving out the industry. So again, so these are the key aspects which is currently driving the adoption of edge computing. So let's look at what are the technologies which we actually need when we actually work on the edge computing. So the key aspects are the containers, the Linux containers. So we actually talked about the edge devices. So these are very lightweight devices, but the key advantage is that most of these devices are running some flavor of Linux, and then Linux supports containers. So you can actually provide containers with specific workload or application, customized containers into these edge devices, and you can manage it so that you will be able to generate the necessary data, collect that necessary data from there, and then ensure that these devices are scaled and are able to match the requirement which is actually they are supposed to do. And then we are not talking about one or two devices here. We are talking about millions of devices. And each enterprise will be having hundreds of thousands of such devices. So who will actually manage it? Can a network administrator go run around and then connect all these devices? That's almost impossible, right? So we need to have orchestration or device management, automated device management solutions, which will actually ensure that these devices are connected, they are configured, they are made available on the network, and they're talking to each other, right? So we need orchestration solutions. And the other aspect is what will we do with all this data which we are collecting? So one of the studies, what McKinsey and company has found was that out of all the data which is getting generated, only 1% is actually used for making some decisions. So the remaining 99% is actually a noise. So how will you filter out that huge amount of data? How will you make value out of the data which you actually collected? So for all those, you need to have artificial intelligence and machine learning models which are available at the edge devices. The 5G, as I said, now it's the key technology which will be driving the adoption of edge computing, because the 5G has provision for high speed bandwidth, low latency, and low power requirement. And then in addition to that, it has the ability to create network of networks and M2M and mesh push model. All those support are available in 5G, so that between the devices they can create networks and they can talk to each other and then connect back to the main network. So there's a lot of provisioning which is actually happening from the 5G. Functional safety mechanisms, that's another key aspect, because we are talking about moving these computation into the devices which are at the factory floor or something like that. And these are the environment in the factory floor and all are literally brutal when compared to the environment available in a data center. So how can we ensure that these devices which we deploy on the factory floor, I mean, are they working properly? Are they doing the right computation? Are they performing correctly? How will we ensure that these rugged devices are ensured to work properly in the environment available in the factory floor? So that will provide the functional safety aspect. Another thing is the time-sensitive networking. So if you think about our Ethernet, it's primarily working on the CSMA, or the carrier sense multiplexers, right? I mean, whether it is collision detection or collision avoidance, whatever be that, these technology is primarily developed with an objective of establishing the connection, establishing the communication. So basically, like you announce your availability, you announce that you have a message to pass, and you will broadcast it, and you will wait for a response, and then you will send it. So there is a lot of backtracking and then again sending it. So there is a lot of time which is involved in sending that message, and in a real-time scenario, this is not acceptable. So what will you do over there? So that's where IEEE came out with the new standard, IEEE 802.1q, which is the time-sensitive networking, or the networking which is sensitive to time. So that's basically, it's a deterministic messaging model, and it is controlled from a central server, so that you will be able to achieve that millisecond latency, below millisecond latency, sub-millisecond latency, and then able to achieve this real-time communication. And finally, with the secure device onboarding, so we are talking about, we talked about these millions of devices which are actually getting deployed. So how will these devices get deployed? Like we said, like having an administrator do all these things, the human intervention, it's not possible. Like if you have a 100,000 devices, how many devices will a person configure in a day maximum? So you cannot humanly achieve it. So that's where you need to have secure onboarding solutions which are available, and then which will ensure that these devices are seamlessly integrated into the network in a secure fashion without any tampering happening over there. So these are the technologies which are involved in getting this edge computation into practice, into actuality. Okay, so let's quickly look at how we will have edge installation or implementation done. So we will start off from the right side where we have the cloud. So that's the cloud model which we currently have. So you collect the data, and this data is actually processed in a cloud. I mean, let it be a private cloud or a public cloud, it's agnostic. I mean, we don't actually worry about it. Let's take it as a hybrid cloud. So the data is coming out from the network edge. As far as the hybrid cloud is considered, the network providers will provide that data from their network edge. That's how they manage the workload. So from these edge devices, one side will connect to the cloud, and the other side will actually connect to the 5G towers, the 5G networks, which will actually create separate networks for the different solutions. Like retail, there will be one network; hospitals, there will be another network; the autonomous traffic, the vehicle traffic, that will be another network. So each of these networks will combine together, will exist coherently, and then that will actually get connected to the network edge. And from these networks, we will have the edge servers, or the high-end devices, or the rack devices, which are actually sitting in the factory floor, where these could be some of these machines which are installed over there to monitor the processes, just to ensure that the processes are running correctly, collect some data to ensure that the productivity is maintained correctly, or to monitor the different devices over there, like the conveyor belt, or the rackers and the stackers and all those things. So these are the devices which are existing in the factory floor, which will provide the computation services, which will have that extra computation bandwidth over there. And finally, the edge devices. These are the small footprint devices which will exist on the actual devices, which will be the smart sensors, or the monitors and the connected devices which are existing on the factory floor. So this is how the connectivity is done. So how will it get implemented? So at the edge device level, we already talked about the containerization. So you have the Linux container running in over there, and then you will be able to provide configure that specific container application onto that edge device, so that it will be able to do the necessary steps over there, and just provide that specific application, or the specific value for which it is actually configured. So it will be able to provide that. And in devices like autonomous car, this is quite possible, because if you look at a luxury car, I mean not an autonomous car, and that on an average contains somewhere around 50 CPUs in that. So think about an autonomous car, and that will be definitely double that number. So 50 CPUs, that much computing capacity is available over there, and easily you will be able to do a lot of processing on that car itself, so that it will be able to collect the data, do the necessary processing, and then get back with the response, then the entire itself, so that you won't be able to you don't need to take into account the latency, or the to and fro travel back to the cloud and getting back. But let's take that to the next level, like where these devices are, the small devices which are existing on a factory floor, on a smart hospital. I mean that sensors or measurement devices and things like that. So if that device is not having sufficient capacity to do this calculation, do this computation, what it can do is it can actually connect to the edge servers which are existing over there. So because all these devices will be connected to an edge server, and in that edge server, it will be able to do this computation over there. So the difference between these two is that both will be supporting containerization. The difference will be that in the edge devices, there will be a single container which will get deployed, and that will be deployed from the edge server. And on the edge server, which is having a more capacity, we will be having more better orchestration management device, like a Kubernetes orchestrator also. That will actually configure all these containers, and then install these services onto the edge devices, and also do the management of it. And then in addition to that, does the computation which is required for the devices which doesn't have that capability to do that. So in short, a good amount of the data which is actually getting generated at the edge device level is getting processed either at the device level itself, or at the edge server level. So that's the key aspect. So in order to manage, and because we said that there will be unplanned spikes and all. So when there are unplanned spikes, because we have a container-based workload model, we will be able to deploy more resources over there, and then we will be able to manage that workload right over there. So the point here is that the consolidation of this data, or the aggregation of this data, makes it that humongous workload which the clouds cannot handle, which our network cannot handle. But if you try to handle that data which is generated by that single device at that device level itself, then you will be in a much better position to manage that data. So that's the essence of cloud edge computing. So once you have all this processing done, Then you will be connecting it through the 5G network to the network edge. And from the network edge, the relevant data will be going into the hybrid cloud where you will be doing the necessary processing. And if there is any requirement, any data which needs to be communicated back to the edge servers or to the edge devices, that will actually come back. So this is how basically the edge computing implementation will happen. So the key technologies which we need to focus here are the Docker, the Kubernetes, the cloud solutions, and we will just look into those solutions in the next slide. So again, like for any solution of this scale to run, what we need is an open source solution, because the open source is the foundation for all the network scalability and the diverse device integrations that we see today. So these solutions, open source solutions, has created some great solutions that helped building the computing industry to this scale. So the innovations actually come out from the open source technology. So again, for the edge computing also, we see a lot of innovations which are coming out from the open source industry. And the key ones are the CIO, which is the Cloud Integrated Advanced Orchestrator. So this is an open source solution which is actually providing a solution to deploy securely and manage these virtual machines and containers on these bare metal devices. So basically, it does all these management, the workload management. CIO is a solution which we can use. The other one with Kubernetes, we already discussed about it. Kubernetes is actually promoted by Google. So that's an open source system for automating the deployment, scaling, and management of the containerized application. So that's the difference. And then the Wi-Fi EC Connect is a open source product, which is actually technology which is actually pushed by the Wi-Fi Alliance, where you can actually get a device brought in to a network, added onto a network seamlessly. Where currently what they do is like you can actually scan a QR code on the device, and then automatically all this configuration and addition to the network will happen seamlessly. Acranio is another open source community product which is actually developing an infrastructure stack for the edge computing solution. The open platform network functionality virtualization, so that open NFV platform, so that they are actually coming out with a lot of solutions for these network virtualization and the SDN NFV technology, which will be having a great use inside the edge computing model, because we need to have a lot of virtualization functions which will be brought into it, because whenever you are adding a new device in, whenever you are creating a new network in, you cannot just go in with the traditional model of having a physical networks solution over the physical routers and physical switches. These cannot be managed at this scale. So what we need is a virtualized switches, virtualized network functions, and on which the SDN NFV technology is providing. So the Open NFV is bringing out a lot of solutions towards that aspect. And finally, the TensorFlow, which is the artificial intelligence library which has been brought out by Google, which we can take and adapt to meet any of our the AI and machine learning requirements. In addition to these open source technologies, the current cloud service providers like the AWS, Amazon Web Services, and Azure from the Microsoft, they are also coming out with managed services for this edge computing solution. A few of them from the AWS are the AWS Outpost, which is a fully managed service that extends the AWS infrastructure, AWS services and tools, everything into virtually into any data center or co-location space or on-premise facilities, and also basically it's an extension of the AWS infrastructure near to the your location. And similarly, there is another solution called AWS Local Zone, which is again currently AWS exists in these different regions. In India also, they have a region in Mumbai, and they are trying to build up another region in Hyderabad. But if you have a high concentration of your industry or your network requirements, edge requirements, what they will do is that they will provide the service of AWS local zone, where you can actually create in AWS infrastructure near to your workplace. AWS Wavelength is another application framework where the developers can build these applications and deploy them for mobile computing with a sub-millisecond latency. The Snowcone and Snowball, they are all part of the AWS Snow family, which that's how they call it. They will provide rugged devices to be incorporated as edge servers or edge devices in the factory floor or in difficult terrains and all, where network is not available or the environment is not suitable and things like that. So using these Snow family devices, we'll be able to bring out the edge connectivity and edge services into that network. The IoT Greengrass is extending the AWS services to the edge devices so that they can locally aggregate on all the data which is getting generated over there. And finally, the free RTOS is a real-time OS which has been created, developed by AWS as a microcontroller device to be implemented, to be installed onto all the embedded devices which we will put over there as connected devices. So these are some of the services which the cloud service providers themselves are now extending towards the edge computing technology, so that we can leverage these services directly on a pay-as-you-go model and then use it. Similarly, for the Microsoft Azure cloud, they provide the edge zones. Edge zones is again like another infrastructure which is actually extending these Azure cloud onto your local service. And there are three types of it, or rather three flavors of it. One is the regular edge zone. The second one is a carrier edge zone, which they will provide it in connection with your carrier, so that if you have a 5G provider, through that provider they will be attaching the edge zone so that you can connect to them. And the third one is private. If you don't want to host your data to a public cloud, then you can actually use the private edge zones. The next one is the IoT Central, which is a hosted application platform to build the secure low latency IoT solutions. The Kubernetes services is a managed Kubernetes service which they provide to have these container services. The DevOps model they are providing to have that continuous integration and continuous deployment model to deploy in fast these applications into the field. AWS virtual machines provide the Linux and Windows virtual machines which you can use for your development. And finally, the Stack Edge, where they provide that complete end-to-end infrastructure stack which you can use to develop your edge services. So these are some of the services which these cloud service providers are currently providing. And finally, to conclude right now, so what are the key things which we saw over here? I'm just putting it all together again. So the key thing is that the world is going to see an explosion, exponential explosion of data traffic in the coming years. So that's something huge, and that's driving the industry, optimizing the computation to computing models to meet that data explosion challenge. The second one is the significant amount of this data is going to be generated by connected devices, which means they are all real-time data. 30% we saw it right now. So when they are generated from the connected devices, it's a machine-to-machine communication. So how will you validate that data? How will you extract the key value from there, key insight from there, and how will you respond back in real time? So all those challenges which are over there. The third one is a latency requirement, which we saw it right now. So there are a lot of requirements of these connected devices need real-time responses. And these real-time responses, the latency, the current cloud model cannot guarantee. And that's the reason why a shift is required. And we are seeing the edge devices coming in. So to meet all these challenges, we have the paradigm shift, and that's edge computing. 5G will act as a catalyst towards adoption of the edge computing technology, and open source is the key, which will drive in all these solutions and technology to bring in the edge computing. And finally, edge computing, the cloud computing is going to stay, but to make cloud computing successful, the edge computing will be working as a catalyst, which will be driving the new world order. So, including that Industry 4.0, which is a smart industry with the automated smart industry. So that's the summary. Um, uh, and then hope you got some essence out of edge computing. Uh, so now we can take some questions.
If anyone have any doubts, you may clear that now.
Hello, sir.
Yeah.
Uh, Sir, thank you for that wonderful session. And I have a doubt regarding the data security in this IoT, because I think security is one of the main research areas in IoT. Like we need better security measures in IoT. How will we assure this data security when we are using this edge computing?
The key aspect itself for bringing in the edge computing is the data security thing. As I said, like the vulnerability of the data is there. You are exposing the data for more vulnerable situation when you increase the surface area of the attack. So if you transfer the data over the network, then you will be having that. Yeah, probably you can mute. If you are transferring the data over the network, then you will be exposing that data, and where it will be getting more vulnerable for that attack. So in edge computing, what they are trying to achieve is that only the relevant data, or only the essence of it, not that individually trackable or traceable data. They don't want to send it over the cloud. So they just want to ensure that the data, to the maximum extent possible, is processed and maintained at the local premise level or at the local device level itself. And there are even, as I said, the hospital requirements are there. Even the European Union has a GDPR requirement where they don't want to put any of the data which is actually traceable back to an individual outside the EU region. There are even stricter requirements like you cannot even collect that data out of the device. So in all those situations, if we are not exposing the data to the maximum extent possible in edge computing, we are not exposing the data outside the edge server, its edge device and the edge server, towards the public cloud side. And when the moment when you are sending that data to the cloud, you will incorporate all the relevant security measures which we currently follow, the encryption, all those things we can actually implement it. So those will be taken care at that level onwards to ensure that the data is safe. But even beyond that, the basic paradigm is that don't send the data so that you avoid the risk of security. Did that answer it?
Okay, sir. Thank you, sir, for that wonderful explanation. Um,
So, thank you, sir. Now, I welcome Ronald Roy of SM CSE to deliver the vote of thanks.
Good afternoon, everyone. I deem it a great honor and privilege to propose the vote of thanks on this occasion. On behalf of the entire institute, I would like to thank our special guest, Mr. Biju Thomas Emsa, who, despite his busy schedule, has found time for this webinar and enlightened us with his knowledge on edge computing. The point where he told us about preventing an incident before it happens by predictive analytics was really interesting. I am pretty sure the precious knowledge that SAR gave us will definitely help us in the future. I would also like to thank our principal, Dr. R.L. Raksa, for giving permission to organize this webinar. Also, we are grateful to our head of the department, Mr. Anubhati Abraham sir, for his guidance and encouragement in all our efforts. Also, my heartfelt thanks to the heads of other departments for accepting our invitation and showing interest in attending this webinar. I owe special gratitude to Mr. Shinumamishan sir, Assistant Professor of Department of Computer Science, who has coordinated this webinar and ensured that this becomes a great success. I would also like to thank all the faculty members and other staffs for their support. Last but not the least, I thank all the students present here for paying attention and learning. Thank you.
Thank you, Ronald. I hope you all enjoyed this session. Thank you.